So, in this video, we're going to look at the concept of a limit, specifically as we can figure it out graphically, how we determine limits and what they mean. We'll look at algebra a little later. So we have a piecewise function here. It's a little bit crazy. It's a bunch of functions put together, but we're going to assume that everything in the purple here is all one function, y equals f at x, with open points to indicate where we have some points that are not included. So we've got a few spots on the graph where that exists. We're going to consider a couple of things. First off, this function is what's called discontinuous, and we have several places where this function is discontinuous, and we'll look at what that means. So continuity, discontinuity isn't necessarily a thing that a function just is or isn't. This function is continuous in some intervals. For example, if I look at the range of the function from, let's say, 8 to infinity, and I consider this function from 8 to infinity, in that range, in that part of the domain, this function is continuous. If I consider the function jumping ahead here. If I consider the function over some intervals where there are no gaps, then it's continuous in that interval. Over its whole domain, though, clearly there are gaps. So we're going to look at the different types of discontinuity in a second. But first, I want us to consider a point where the function actually is continuous so that we can consider what it means mathematically, the formal definition to be continuous. So we're going to look at what happens when f equals 2. So if I look at the point where f equals 2, then I'm concerned for continuity, not just 2, x equals 2, but also the immediate environment around that point. And just from a non-formal, non-rigorous standpoint, if I look at that and just sort of zoom in on that part of the graph, everything I've highlighted in yellow there, it is continuous. There are no gaps or breaks in that point. There's a sharp angle, but that's not really relevant right now. So at 2, the value of the function, so f at 2, is equal to 3. That's the y value at that point. But in order to define continuity, I have to consider something called a limit. So the limits are basically not exactly what is happening at 2, but what is happening as I get close to 2. So there's 3 different ways this can be expressed if I look at these 3 different limit notations I've written here. So the limit as x approaches 2, and then the little negative sign beside the 2. So right here, if I'm looking at this, what that means is x is approaching 2, but from the negative side. In other words, from the left. X is approaching 2 from the side that is less than 2. So from this direction that I've just highlighted in blue. So what I'm wanting to know then is, if I were to ignore exactly what's happening at 2, what does the graph seem to be doing? What does the y value seem to be getting close to? And here, in this case, it's actually really easy because that segment of the graph is just the horizontal line y equals 3. So if I look at, well, what is the value of y when x equals 1? What is the value of y when x equals 1.6, 1.7, 1.8, 1.9, 1.99, 1.999? All of those points, y equals 3. So the limit as x approaches 2 from the left of this function is 3. The next limit is the right-hand limit. So limit as x approaches 2 with a little plus sign means I'm approaching from the right, so from the positive side. So from the right-hand side. Again, I'm not actually looking at 2. I'm looking what happens if x is close to but not exactly 2. So 2.001, 2.0001, 2.000001. It's getting closer and closer to 2, but it isn't actually 2. What then is happening to the y values? Now, in this case, the y values aren't all the same. The y values are, so for example, if I have 2.5, then the y value is somewhere around here, around 3.7. If I have y equals 2.25, then the y value is somewhere here. But what I see as I get closer and closer to the 2 is that the y value gets closer and closer to 3. So the right-hand limit here is also 3. Now, this is critical, and we'll see several examples where this isn't the case. The right-hand and left-hand limits have to be the same in order for this next limit to exist. So because as I approach 2 from the left and as I approach 2 from the right, I am approaching the same value. In both cases, the limit is 3. then I can say the limit as x approaches 2 equals 3. So if there is no minus or plus there, it means from either side. It doesn't matter if I'm slightly less than 2, 1.99999, for example, or slightly more than 2, 2.00001. Whichever side I approach from, I'm getting closer and closer to 3, so the limit is equal to 3. Now, this is where the definition of continuity comes in. A function is continuous if f at that value, so in this case f at 2, equals the limit as x approaches 2 from both sides, basically, of f at x. So the function, in other words, as I approach from the left, it seems to be leading to 3. And as I approach from the right, it seems to be leading to 3. And then when I actually look at the value of 2, hey, no surprises, it is 3. This means that f of x is continuous at 2. So continuity is what happens in specific points. And we're going to look at some points where it's definitely not continuous. So for example, if I just look at this graph, I can tell, for example, that at -10, this function is not continuous. Oh, I'm actually missing a point on here. There should be a point right here. So at -10, it is a function because when x equals -10, y equals 1. That's the point I just drew on. And because of the open circles on the ends of the other segments, I can see that it doesn't include -10. So this curve right here goes up to, but not quite -10. So -10.00001, sure, but not -10. And this line segment on the right-hand side includes everything up to -10, but not -10. So we have a function, but it's clearly broken. The function breaks apart. It breaks apart at -5, it breaks apart at -2, it breaks apart at 4, and there's an open circle when x equals 5. So all of these are discontinuities. So we're going to look at how we can tell formally that they are discontinuities and what type of discontinuities they are. So let's start with -10. So at -10, the value of the function is 1. So that's the point that I drew on most recently, -10, y equals 1. But if I am approaching -10 from the left, in other words, here, what does it look like the function is going to? Now, bear in mind that f at 10 never actually reaches this open circle here, but the coordinates of that open circle are -10, 5. So the limit as x approaches -10 from the left is 5. As it approaches from the right, it seems to be going to this open circle. Again, it doesn't actually get there, but the coordinates of that open circle are -10, 8. So the y value is approaching 8 as we approach -10 from the right-hand side. Important to note here, those two are not equal. The left-hand limit and the right-hand limit do not equal each other. So there is no limit. We can't just say, what is the limit of this function as x approaches -10? It does not exist. That's what this symbol means. It does not exist. Because it's going to a different place from the left and a different place from the right, and they don't match up. So in this case, f at a does not equal either of the limits. Even if it did, it still wouldn't necessarily be continuous. But it doesn't equal the left-hand limit. It doesn't equal the right-hand limit. Because the left and right-hand limits don't equal each other, there is no limit, no just overall limit. So this is definitely discontinuous. Everything is different. And it doesn't have a special name. No special name. Some of the other ones do. It's just discontinuous. All right, now let's look at what happens when x equals -5. When x equals -5, we actually have this value right here. So when x equals -5, y equals 0. Approaching from the left, it's actually connected. So as I approach from the left, it does seem to be going to 0. So the limit as x approaches a from the left is 0. It's going exactly where I expect it to go because that point is connected to that section. But if I look here, I have a vertical asymptote. So if I'm approaching from the right-hand side, the limit doesn't actually reach a number. It actually just goes off to -infinity because it just keeps going down, 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 down towards that asymptote. So these are definitely not equal to each other. So this limit, the limit as x approaches -5, does not exist. So even though the value of the function is connected here, because it doesn't equal the right-hand limit, this is a discontinuous function. And in this case, the discontinuity is an asymptote. So asymptotes are a type of discontinuity. Considering now what's happening at -2. Well, something kind of similar. -2, that point is connected to one of the lines. So when f at -2 is 1, the limit as we're approaching from the left-hand side, well, that's connected, so it's approaching 1. But as I'm approaching from the right-hand side, it's 3. So in spite of the fact that the value of the function is equal to one of the sided limits, it does not equal the other side limit. So the overall limit doesn't exist. And this is a discontinuity. The type of discontinuity here is called a step discontinuity. Step or jump sometimes, but it's a step up. We just suddenly break. It is connected on one side, and then it jumps to another point. When we look at 4, something very similar happens. So the value of the function at 4 is 0, because that is where I have the solid line. So the value of the function at 4 is 0. From the left-hand side, though, that's not where I'm going to. From the left-hand side, as I approach 4, I'm going to a y value of 6. So the left-hand limit here is 6. The right-hand limit, on the other hand, as we approach from the right, it is going to 0 because it is connected there. So in spite of the fact that the value of the function equals the right-hand limit, the two limits do not equal each other. So the overall limit doesn't exist. So this is also a step discontinuity. So if I look at the graph, my function is connected on one side, but there's a gap, there's a jump. It's like it's taken a step up or a step down. Now considering what is happening at 5. So 5, I just have an open circle. So the function actually doesn't exist at 5. This would be a domain restriction. In fact, for this particular function, the overall domain is x such that x does not equal 5. But other than that, x can be any other real number. Because if I look at what's happening here, assuming that there are arrows on these endpoints, it exists at every other value. Even that vertical asymptote at -5, it still exists because I have a solid point on the axis. The only point where it doesn't actually exist is at 5. So the function doesn't exist at 5. But the limit does, because whether I am approaching from the left or the right, if I'm approaching it from the left, it seems to be going to this point. And if I'm approaching from the right, it seems to be going to that point. That point is an open circle. So f at 5 does not exist. But as I approach it from the left, it seems to be going towards a value of 1. As I approach it from the right, it seems to be going towards a value of 1. These two limits are equal to each other. The left-hand limit equals the right-hand limit. So overall, there is a limit. The limit at this point does exist. When the limit exists, but the function doesn't, this is a point discontinuity. So you have encountered these before. A point discontinuity is where you have a limit that exists, but the function that doesn't. So that's a point discontinuity. I also just briefly want to discuss the limits at infinity. So in other words, as x goes to infinity. Now, obviously, I can't approach infinity from both sides. If I'm approaching positive infinity, I can only approach it from the left. I can only have numbers that are less than it. If I'm approaching negative infinity, I can only approach it from the right. So just overall, we don't worry about one-sided limits for infinity. You can't get around the other side of infinity. So the limit as x approaches infinity. So I look at my graph and I consider, as x gets bigger and bigger and bigger, what does y seem to be becoming? And this is where the horizontal asymptote comes in. The horizontal asymptote represents a limit as x approaches infinity or as x approaches negative infinity. So in this case, the horizontal asymptote is when y equals 2. So the limit as x approaches infinity is 2, and negative infinity is not quite as obvious on the graph, but it is in fact going down to that asymptote as well. So as x approaches negative infinity, the limit of this function is also 2.